Hello everybody, this is Jeff Janess again, continuing our lecture on geoprocessing and on models and environments. And last video we talked about basic geoprocessing. We looked at some of those geoprocessing tools. We showed you how to use them and set them up to run, set the parameters. Well, today we're going to move on to environments. And environmental settings just give you more ways to run these tools. For example, whenever you run a tool in ArcGIS Pro, you have to tell the tool a few things. In ArcGIS, these things are referred to as parameters. So for example, when you run the buffer tool, you need to specify parameters for the input feature class, the output feature class, the distance, the units of the distance, optionally some buffer shape types, optionally whether to use geodesic or planar distances, and optionally whether you're going to dissolve anything. You click Run and the tool goes. However, there are actually several more parameters that ArcGIS can use in the analysis that are not revealed in the tool dialog. And these things are called environments, and they give you a lot more control over exactly how the tool is run. Now, not all tools honor all environmental settings, but if a tool can honor a setting, then these settings will show up in that tool's environments pane. For example, the buffer tool uses these 6 environmental settings, while the slope tool uses these 5. Each tool shares the output coordinates and the processing extent settings. If a tool does support an environment, it'll usually say so at the bottom of the help file for that tool. So let's look at some examples of environments. Starting off with workspaces. You have current and scratch data locations. You can set these to somewhere you actually have room, like your bonsai drive if you're on the NAU system. Your current workspace is similar to your default geodatabase and is initially set to the same location. Your scratch workspace is where you might generate temporary intermediate data. And in fact, a lot of the tools, while they're working, they actually generate intermediate data while they're processing. So the tool itself will use that scratch workspace to decide where to save stuff. In those cases, those scratch data sets are automatically deleted as soon as the tool is complete. Now, ArcGIS Pro initially sets your current and scratch workspace to be that same geodatabase that's created with your project, but you can change these if you want. And in fact, our first lab exercise will see how to do exactly that. Output coordinates is a good one. Lets you force all your new data to be in a particular coordinate system. Forces the data to be projected if it's not already in that specified coordinate system. The processing extent lets you restrict your new data to a particular geographic area. And this kind of thing is useful when your data sets cover a large geographic area, but your analysis is focused on a smaller area. Now, the raster analysis parameters are important when a tool uses more than one raster. So there's lots of times when rasters have different cell sizes, for example. And so what would you expect to happen when you're going to do an analysis on 2 rasters and these rasters have different cell sizes? This slide shows a fairly typical question you might ask. If you have an elevation raster and you have a slope raster and you just want to know what parts of the landscape are above a certain elevation and have a certain slope range, and it's a pretty simple analysis, but it gives you a new raster that tells you where those conditions are met. And the question becomes, well, if your initial data sets had different cell sizes, what cell size will the new raster have? So this cell size parameter lets you specify that value. The mask parameter lets you clip all your new rasters to some region of interest without using the extract by mask tool separately. However, the mask parameter doesn't work on some rasters like those produced by the cost distance tool, so just be aware of that. You'll always get a full-size raster with that tool. But if you want to clip it to an analysis area, you'll need to do that in a separate step after you create the original raster. The Snap Raster setting is another important environmental setting when working with rasters, and this one addresses an issue that has caused people lots of trouble over the years when working with raster data. Problem is that you do some process or analysis to your raster, and the new raster has all the cells shifted over a little bit. You may or may not care about that, but if you do, then you can get kind of annoyed with it. And the deal is that when these raster tools run, they produce a new raster, and they have to decide what the origin point of that new raster is. Remember, a raster is just a bunch of rows and columns of cells, and the origin is the upper left corner of the raster. Rows and columns are then built out from that origin point. So the tool has to decide where to place that origin point before creating the raster. A lot of times when you're doing some analysis with a raster that involves a vector object, the tool will decide the origin point based on the upper left corner of the rectangular extent that contains the vector object. If that new origin doesn't align perfectly with the original raster and it rarely does, then the cells wind up slid over like this. And like I said, this may or may not be a problem when you do a single tool, but it can be a problem when you're doing several functions in a row. If it slides this much with one run of the tool, then will it slide that much again with the next run? And eventually, who knows where the rasters get slid to? You really have a lot of potential to lose significant spatial precision when the rasters slide around like this. Now, this issue of shifting raster datasets when you analyze them is kind of an important issue, and I'd like you to really understand what's going on. So let's do a quick demonstration. Now, in this map, I've loaded up some climate data showing the mean precipitation across the continental U.S., and if you're curious, this happens to be monthly precip of July of 2021 during monsoon season last year. And by the way, if this kind of data looks useful to you, I got this PRISM data from Oregon State University. PRISM's got really great climate data. It offers minimum, maximum, mean temperatures, precipitation levels, mean dew point temperatures, vapor pressure deficits, all summarized monthly and daily all the way back to the 1890s. Now, obviously, the weather stations were more sparsely distributed back in the 1890s, so the more recent years are more likely to be accurate. But if you're looking for climate and weather trends, then PRISM's really great data. So anyway, I have this PRISM data. It covers the entire continental United States, but maybe I'm only interested in the Coconino National Forest down here. Just pop that open here. Yeah, I'm just doing analysis on the Coconino. So when I do my analysis, why would I also want to be analyzing data up in Maine or Florida or up in Washington? It just takes extra processing time, fills up my hard drive faster, and I'm only going to be looking at the results in the Coconino anyway. So it'd be nice to just be able to restrict my analysis to just the Coconino. Now this is a case where we can set our processing extent environmental setting. And so that's what I'm going to do. Just to make this a little easier to see, I'm going to zoom into the Coconino. This is a close-up. At this map extent, you can see the individual raster cells that underlay the Coconino. And by the way, these cells are at 4-kilometer resolution. That's the resolution that PRISM offers for free. And by the way, you can actually purchase a higher resolution version of PRISM data if you want. The source data is actually at 800-meter resolution. Personally, I've never had the money for that, so I've just used the 4-kilometer version. Now, to demonstrate this problem of shifting rasters, I'm just going to run a fairly standard raster analysis tool. And the tool we use in this example really doesn't matter so much. I'm just showing you how these tools tend to shift rasters when they do their thing. We're going to open up the Focal Statistics tool. We'll learn more about the Focal Statistics tool in a later course, but basically what it's doing is looking in a neighborhood around each cell and producing a new raster in which the raster value is equal to some statistic describing that neighborhood of cells. So maybe I want to know the average precipitation within several cells around each cell and make a new raster showing those averages. Well, Focal Statistics is the way to go. So I'm going to open up the Focal Statistics. I'm going to drag in my precipitation raster. The output, I'm just going to call it mean precipitation. We'll just use a circular neighborhood with a radius of 3 cells. It doesn't really matter. We're just demonstrating the shifting rasters here. Now, remember, this precip covers the entire United States, so I'm only interested in the Coconino. Why don't I just tell it to only analyze within the Coconino? I can do that by going to the environments, setting the processing extent right here to be the Coconino National Forest. So I can set it right to one of my layers. All right, that should be good to go. We hit Run. It goes and generates our raster. It does it a lot quicker than it would have done if we did the entire country. Let's close this tool. And now here is our new raster. Now the problem here, if we zoom in, we can see clearly that the raster cells do not line up. So this cell here in the new raster will represent the average precipitation value in a neighborhood around this cell here in the old raster. So the mean cell got shifted over by a certain amount. If we're curious about how far did it get shifted over, we can just go to our little measure tool and just measure distance, draw. So it got shifted by over a mile to the southeast. That's quite a shift on our raster cells there. Now, if we did this again, could get shifted even more. If this isn't a problem for your particular analysis, then that's fine, but it can get to be a problem, and especially if you start doing more operations. Maybe each new raster will keep getting shifted to the southeast, and eventually you start getting data that is just far removed from the source of where it was originally being analyzed. So that's what this Snap Raster thing is all about. I can force my new raster to perfectly align with the original raster. So let's zoom back to our last extent. We're going to rerun the tool, but this time we're going to set a Snap Raster. I'm going to turn that off. Let's go to our Analysis, Tools, Focal Statistics. Do the same thing again. This one I'm going to call Mean Raster Snapped. Again, it'll be a circle, 3-cell radius. We go to our environment, set the processing extent to be the coconino. But now the Snap Raster. Let's pop down here in the raster analysis section. Snap Raster. I'm going to snap it to the original prism data. Just like that. Hit run. Now it produces a new raster. If we zoom in, we can see that the new raster perfectly aligns with the original raster. So we can be a lot more confident that the mean values in this new raster truly represent the means of the neighborhoods directly underneath those cells. Now, environmental parameters apply to both tools and to models, and they're actually hierarchical. There's 4 levels of environmental settings. The first level is the application level. You can actually set environmental settings within ArcGIS Pro itself, and it's stored with your project. You can also set these settings at the tool level, and if you do that, the tool level will override the application level. The issue here is that you can set environmental settings that conflict with each other. Maybe your application level environmental setting says that all tools will export data into the UTM coordinate system, but then when you run a tool, you can set the tool environmental setting to say that this tool produces data in, say, Web Mercator. Well, you got 2 environmental settings that are fighting with each other. The tool level one will override the application level one, but the tool level only lasts for a single run of the tool. The application level setting, it's saved right into your ArcGIS project. So it'll even be still set if you close your project and reopen it later. Now you can store it in a model, and we're going to talk about models soon, but the model itself can have an environmental setting, and then the tools within the model can have an environmental setting. Well, the tools within the model will override the model level settings. Now, to get to these settings and the application level settings, you get to it from the Analysis tab, then you go to the little Environments button. But be careful with these application level settings. They can trip you up if you're not careful. Remember that they're written right into your project, so if later on you do some analysis and you forget that setting is there, well, you might get unexpected results from your tool. Now, I even had an experience with this that caused me a lot of grief a few years ago. I was analyzing some fires in Arizona and New Mexico. 2 of these were the Wallow Fire on the Apache Sitgreaves National Forest, you see on the left here. Over here in New Mexico was the Miller Fire on the Gila National Forest. Now, I was spending a lot of time on each fire, and I was using some road feature classes and some climate rasters that covered the entire country. It was kind of running slow, and I thought I'd make it easier on myself by setting the processing extent to the region right around the fire boundaries. And that actually worked great when I was working on the Wallow Fire, but when I moved on to the Miller Fire here, I forgot I'd set those application environments. Every tool I ran would say it ran successfully, but it produced empty data sets. It took me quite a while to figure out that my processing extent environment setting was still set for the Wallow, and so all this Gila data I was working on just didn't exist within the extent of the Wallow. It was just getting clipped out. Eventually, I remembered to just reset the processing extent for the Miller Fire region, and everything worked fine after that. Here's a good example of an application-level environment setting. You can set your default geodatabase for this ArcGIS Pro project pretty easily, letting you avoid your C drives on the NAU system, for example. And you can set this environment setting by just connecting a geodatabase with your project and then just right-clicking on the geodatabase to set it to the default. And you'll do this in the first lab exercise. But remember, this is only saved with the project. If you open a new project, you'll have to reset the default geodatabase again. Although there is an exception to this rule, there is a general setting in the ArcGIS Pro options that will let you designate a single geodatabase as the default for all new ArcGIS Pro projects. But if you do reset your project default geodatabase the way we just described, where you right-click on the geodatabase and make it default, then if you go and open up your application level environments window, by going to the Analysis tab and hitting Environments, you'll see that the current and scratched geodatabases have been set to this default geodatabase. Now, tool level settings override the application level settings, but they only last for a single run of the tool. For example, if you open a tool like this Extract Values to Points tool in the slide, then you can click the Environments command to set environmental parameters for this single run of the tool. If you run the tool a second time, you'll need to set the environment settings a second time. Model level settings apply to all tools and processes in the model. The window looks exactly the same as the application level settings window, but you get to it from the Model Builder tab. And then within the model itself, you can set a model tool setting. And this applies to a single process in the model. It overrides any application and general model environment settings that you might have. Okay, now let's think about the consequences of these hierarchies. And I have 4 questions here to try and nail it down. And these questions will also be on your homework. So if you can answer them here, it'll be easier to answer them on the homework. Okay, so let's look at a situation. Suppose we have a roads feature class for the Coconino National Forest, and these roads are in UTM Zone 12 coordinates. They're projected from NAD 83. We want to run the buffer tool and generate some buffers around them. We aren't going to set any specific environmental settings. We're just going to run the buffer tool as is. And when it produces the buffers, what coordinate system will those buffers be in? Now, with no environmental settings set, there's no reason for ArcGIS to do anything special with this, so it stands to reason that the new buffers will be in the same coordinate system as the source data. Hopefully that makes sense. Now let's try another question. Let's start adding some settings. We set our application level output coordinates environmental setting to North American Lambert Conformal Conic. This means that the tools that you run will produce data in Lambert Conformal Conic. Now our roads are still in NAD 83, UTM Zone 12. We run the buffer tool, we generate our buffers. What coordinate system will they be in? Well, hopefully it is clear that by setting the application level environmental parameter, all tools that you run in this ArcGIS Pro project will produce data in this Lambert Conformal Conic, no matter what coordinate system they started in. So the answer would be North America Lambert Conformal Conic. All right, let's start complicating things. Again, we've set our application level coordinate system to be conformal conic, as did before. Our roads are still in UTM Zone 12. But when we open up the buffer tool to run it, we set the tool level output coordinates to Web Mercator Auxiliary Sphere. So this means that we've set up conflicting environments. Our application is trying to convert it to Lambert Conformal Conic. The tool itself is trying to convert it to Web Mercator Auxiliary Sphere. So who's going to win? What coordinate system will the buffers be in? Well, remember that the tool setting overrides the application setting. So if you've got a conflict there, the tool is going to override the application. Therefore, in this case, the buffers will be in the Web Mercator Auxiliary Sphere. All right, let's try it one more time. We set it up the way we did before. Applications in North America, Lambert. The rows themselves are in UTM Zone 12. We open up the tool. We set the tool parameters to produce data in Web Mercator Auxiliary Sphere. Then we run it and generate some buffers. But then we open the buffer tool a second time. This time we're not setting any special tool levels parameters within the tool. We generate the buffers. And what coordinate system will the second road buffer feature class be in? Okay, so now we're getting at how long does a tool environmental setting last. The application level will last as long as your project is open, and if you save your project and reopen it, it'll still remember your application level settings. The tool setting, however, only lasts for that single run of the tool, and then ArcGIS Pro forgets it. So when we open the buffer tool the second time, well, it's going to revert back to the application level settings. Therefore, the second road buffer feature class is going to be in the North America Lambert Conformal Conic. All right, hope that makes sense. Okay, and I think that's about what I'd like to say about environments and the hierarchy of environmental settings. So I think we'll close this video off here, and next video we'll pick up with Model Builder, which is a really clever and easy way to string multiple tools together. Really cool function, and I think you'll enjoy it. All right, thanks so much.